G'day, mates. Have you ever looked up at the night sky, at that vast, dark canvas sprinkled with countless stars, and felt a profound sense of wonder? It's a feeling that connects us all, a question that has echoed through human history for millennia. Are we alone in this immense universe? This question isn't just a fleeting thought. It's a deep, driving curiosity that pushes us to explore, to discover, and to understand our place in the cosmos. We've sent probes to distant planets, pointed powerful telescopes towards faraway galaxies, and listened intently for any faint signal from the stars, all in the hope of finding an answer. This quest for cosmic company often leads us to search for worlds like our own. We look for planets that are rocky, about the size of Earth, and orbiting their star at just the right distance, the so-called Goldilocks zone. Let's take a moment to really think about our home, Earth. It's a beautiful blue marble, a haven of life in the cold vacuum of space. We have stable ground beneath our feet, vast oceans of liquid water, and a relatively mild atmosphere that shields us from the harshness of space. When we search for life elsewhere, we instinctively look for these familiar conditions. We hunt for planets with similar gravity, a breathable atmosphere, and temperatures that allow water to flow freely. But the universe is not just a collection of Earth-like planets. In fact, worlds like ours might be relatively uncommon. The cosmos is filled with an incredible diversity of planets, many of which are wildly different from anything we know. And then there are the gas giants, the true titans of planetary systems. These worlds are fundamentally different from our own. They are immense spheres of gas and liquid, with no solid surface to stand on. This brings us to a truly mind-bending idea, a concept that feels like it's been lifted straight from the pages of science fiction. What if we've been looking in the wrong places altogether? What if life isn't clinging to the solid ground of a rocky planet, but is instead floating freely, high up in the clouds of a world with no surface at all? We're talking about the gas giants, the colossal swirling behemoths of our solar system and beyond. What exactly are we talking about when we say gas giant? These are planets made primarily of gases, not solid rock like our Earth. They are colossal, absolute monsters compared to the rocky inner planets. Imagine trying to fit Earth inside Jupiter. You could cram over 1,300 Earths in there and still have room to spare. These giants are mostly made of the lightest and most abundant elements in the universe, hydrogen and helium. It's the same stuff our sun is made of. Think of them as stars that never quite made it. Failed stars that didn't gather enough mass to ignite nuclear fusion in their cores. Now, the most crucial difference between a gas giant and a planet like Earth is the lack of a solid surface. If you were to try and land a spaceship on Jupiter, you wouldn't find any ground to touch down on. You would just keep falling, descending through endless layers of clouds. The atmosphere just gets thicker and denser and hotter the deeper you go. The pressure would build up to unimaginable levels, eventually becoming so intense that it would crush your spacecraft like a tin can. There's no there, no solid place to stand, just an endless sky. When we look at our own cosmic backyard, we've got two magnificent examples of gas giants holding court: Jupiter and Saturn. Jupiter, the larger of the two, is a true behemoth. Its presence has shaped the very architecture of our solar system, its immense gravity acting like a cosmic bouncer, flinging asteroids and comets around and protecting the inner planets, including us, from constant bombardment. And of course, it's home to the most famous storm in the solar system, the Great Red Spot. The Great Red Spot is an anticyclone, a storm that has been raging for at least 400 years, and it's wider than our entire planet. Just think about that for a moment. A single storm, larger than Earth, that has been going for centuries. Then you have Saturn, the jewel of the solar system. While it's a bit smaller than Jupiter, it's famous for its breathtaking system of rings. These rings aren't solid. They're made of billions of individual particles of ice and rock, ranging in size from tiny dust grains to chunks as large as a house. Both Jupiter and Saturn have their own miniature solar systems of moons, dozens of them. Some of these moons, like Jupiter's Europa and Saturn's Enceladus, are considered top candidates for finding life, but in their subsurface oceans, not in the clouds. However, the planets themselves present a different kind of possibility. While Jupiter and Saturn are impressive, They are just the local examples. Thanks to our powerful telescopes, like the Kepler Space Telescope, and now the James Webb Space Telescope, we've discovered that gas giants are incredibly common throughout the galaxy. We've found thousands of them orbiting other stars. These distant worlds, known as exoplanets, come in a stunning variety. Some of these alien giants are what we call hot Jupiters, massive planets that orbit incredibly close to their parent stars. There are cold Jupiters or super Jupiters, which are much more like our own. We've even found rogue planets, giant worlds that have been ejected from their original solar systems and now wander alone through the cold, dark emptiness of interstellar space. This incredible diversity is what makes the search so exciting. Each new discovery of a gas giant exoplanet adds another piece to the puzzle. We can study their atmospheres from afar by analyzing the starlight that passes through them, looking for the chemical signatures of molecules like water, methane, and ammonia. With every new world we find, we expand the realm of possibility. The question is no longer just about Jupiter or Saturn. It's about the countless giant worlds scattered across the Milky Way, each one a unique and mysterious kingdom of clouds. Imagine you're in a probe, beginning a one-way journey into the heart of a gas giant like Jupiter. As you descend, you leave the blackness of space behind and enter the upper reaches of the atmosphere. At first, it's a thin, hazy layer of hydrogen and helium, bitterly cold and seemingly serene. But this calm is deceptive. You are entering a world whose scale is almost impossible to comprehend. The sky above isn't a simple blue dome like Earth's. It's a multi-layered, planet-spanning ocean of gas that stretches down for tens of thousands of kilometers. This is not just a weather system, it's the planet itself. As you continue your fall, the pressure and temperature begin to climb steadily. You pass through different layers of clouds, each with its own distinct composition and color. The highest clouds you encounter would likely be made of ammonia ice, appearing as bright, white, cirrus-like formations against the deeper colors of the planet. Below that, perhaps 100 kilometers from where you started, you might reach the third and most intriguing cloud deck, clouds of water ice and, deeper still, liquid water droplets. This is the region that excites astrobiologists the most. Here, for a fleeting moment in your descent, the conditions could be surprisingly familiar. The skies of a gas giant are not just layered, they're dynamic and, well, violent on a scale that absolutely dwarfs any weather system on Earth. Our most powerful hurricanes would be, honestly, just little eddies in the colossal jet streams that circle these giant worlds. On Jupiter, winds between the different colored bands can reach speeds of over 500 kilometers per hour. The most famous feature, Jupiter's Great Red Spot, is the ultimate testament to this atmospheric violence. It's a swirling vortex so vast that it could honestly swallow our entire planet with ease. For centuries, this colossal storm has churned through Jupiter's southern hemisphere, a permanent hurricane of staggering proportions. This extreme weather creates a dramatic and constantly changing environment. The colors we see are the result of complex chemistry, where different compounds are dredged up from the depths by powerful convective currents and then exposed to sunlight. This solar radiation can trigger chemical reactions, creating the chromophores, the color-bearing molecules, that paint the clouds in their distinctive shades of red, orange, brown, and yellow. For any potential life, these storms would be both a hazard and an opportunity. The sheer violence could tear any organism apart, but the massive updrafts within them could also be a vital lifeline. These currents could transport nutrients and chemicals from the deeper, richer layers of the atmosphere up to the habitable zone. When we strip it all down, the question of life comes down to a few key ingredients. You need raw materials, an energy source, and a liquid solvent, most likely water. Remarkably, the atmospheres of gas giants seem to have all three. The raw materials are there in abundance. The skies are a rich soup of hydrogen, helium, methane, ammonia, and, crucially, water vapor. These simple molecules contain the essential elements for life as we know it: carbon, hydrogen, oxygen, and nitrogen. Gas giants have energy sources in spades. There's the powerful ultraviolet radiation from the sun beating down on the upper cloud layers. But more dramatically, there is lightning. Probes like Voyager and Juno have detected superbolts of lightning on Jupiter that are hundreds of times more powerful than any lightning on Earth. Finally, there's the need for a liquid solvent, a medium where chemical reactions can take place. And as we've discussed, deep within the chaos, there exists that potential habitable zone where temperatures and pressures are just right for liquid water droplets to form. So, we have a potential home for life, a narrow, temperate layer in the sky. We have the right ingredients and the energy to spark things off. This is where science starts to blur with imagination, but it's a form of disciplined imagination, grounded in the laws of physics and biology. The legendary astronomer Carl Sagan was a pioneer in this area. First, they imagined the primary producers, the equivalent of plants in this ecosystem. They called them sinkers. These would be tiny, microscopic organisms, too small to fight the currents. Their life would be a cycle of falling and rising. They would reproduce in the upper, sunlit layers of the habitable zone, then slowly sink into the hotter, deeper regions. Building on that foundation, Sagan and Salpeter imagined the giants of this world, the floaters. These would be colossal creatures, perhaps kilometers across, like living hot air balloons or zeppelins. They would be, in essence, enormous, self-propelled gas bags. They might generate their own internal heat by metabolizing food, which would heat the hydrogen gas inside their bodies, making it lighter than the surrounding atmosphere and providing lift. To complete their ecosystem, they conceived of hunters. These would be smaller, faster, and more agile than the floaters. They wouldn't need to be buoyant themselves. Instead, they would be like living fighter jets, using aerodynamic lift and powerful propulsion to maneuver through the dense air. They would be the carnivores of this airborne world, preying on the floaters and perhaps on each other. So you have food and you have energy. But in a world with no ground, the single most important challenge for any life form is simply to avoid falling. Gravity is relentless. On Jupiter, it's about 2.5 times stronger than on Earth. Any organism would be in a constant battle against being dragged down into the crushing, scorching depths where life is impossible. Survival would depend entirely on mastering the art of buoyancy. The most straightforward method is the one Sagan imagined for his floaters, the hot air balloon principle. For smaller organisms, a different strategy would be needed. They could be more like plankton in Earth's oceans, organisms that use their shape to slow their sinking, evolving to have very large surface areas compared to their mass, like living parachutes or kites. This whole idea of life in the violent, chaotic skies of a gas giant might still sound like pure fantasy. But before we dismiss it as impossible, we should take a good, hard look at our own world. We often think of Earth as a paradise, a perfect haven for life. But the truth is, life here has conquered environments that are incredibly hostile and extreme, places that would be instantly lethal to you or me. These tenacious organisms, called Extremophiles, are a powerful testament to the sheer resilience and adaptability of life. We have found life that can withstand crushing pressures at the bottom of the deepest ocean trenches, pressures far greater than those in the habitable cloud layers of Jupiter. We have found life that can survive incredible doses of radiation, enough to sterilize our medical equipment. We don't even need to go to the deepest oceans or the driest deserts to find life in extreme airborne environments. We just need to look up. Our own atmosphere, the sky above our heads, is not sterile. It is teeming with life. Microbiologists have discovered a vast and complex ecosystem of bacteria, fungi, viruses, and pollen, floating high above the ground. This discovery is profound when we think about gas giants. It provides a direct, real-world analog for the sinkers that Carl Sagan imagined. It proves that a microbial ecosystem can exist in an atmospheric setting. While Earth's microbes are just temporary visitors to the sky, it's not a huge leap to picture a world where this becomes permanent. Another one of Earth's extreme environments provides a powerful parallel for life on a gas giant, not in the sky, but in the crushing blackness of the deep ocean. Miles below the surface, where no sunlight has ever reached, we discovered one of the most profound biological insights of the 20th century. Around volcanic hydrothermal vents on the ocean floor, entire ecosystems thrive in complete darkness. These communities are not based on photosynthesis. Instead, they are built upon a foundation of chemosynthesis. Bacteria and archaea here harness the chemical energy from compounds like hydrogen sulfide spewing out of the vents, turning volcanic chemistry into the energy of life. This discovery was revolutionary. It broke our dependence on sunlight as the sole source of energy for a complex ecosystem. This is a crucial piece of the puzzle for gas giants. The parallels are striking. On a gas giant, the planet's internal heat drives powerful updrafts, bringing a rich mixture of chemicals up from the deep interior. These updrafts are, in a sense, like hydrothermal vents flipped upside down. Instead of erupting from the seafloor, they erupt into the sky. A floating ecosystem could cluster around these atmospheric upwellings, just as life clusters around vents on our ocean floor, drawing energy from the planet's own geological and chemical activity rather than from the distant sun. The deep ocean has taught us that where there is a source of chemical energy and liquid water, life can find a way to flourish, even in conditions of immense pressure and total darkness. While it's exciting to imagine these exotic ecosystems, we have to be realistic. The challenges facing any potential life on a gas giant are immense, perhaps the most extreme in the entire solar system. The first and most fundamental hurdle is gravity itself. Every part of an organism's life would be a constant energy-sapping battle against being pulled down into the planet's deadly interior. Even if an organism could solve the problem of gravity, it would then face the next great challenge, the sheer violence of the atmosphere itself. The skies of a gas giant are not a calm, serene ocean of air. They're a maelstrom of chaotic motion, with winds and storms that make Earth's most powerful hurricanes look like gentle breezes. Let's say, just for a moment, that a life form has mastered buoyancy and can navigate the violent winds. It still has to contend with the very air it's floating in. While we've described the atmosphere as a rich chemical soup full of the building blocks of life, many of these chemicals are also highly corrosive and toxic from our perspective. Any life here would need a biology that is fundamentally different from our own, with biochemistry capable of withstanding this chemical onslaught. Surviving in the clouds of a gas giant is a constant balancing act, trying to get enough energy and nutrients from the environment without being destroyed by it in the process. Right then, we've explored the wild possibilities, the mind-bending challenges, and the tantalizing clues. But how do we go from educated guesswork to actual discovery? The only way to get that evidence is to go there. This means designing and launching a new generation of robotic explorers, missions specifically created to dive into the very hearts of these giant, stormy worlds. The dream mission, the one that gets astrobiologists really excited, is a dedicated atmospheric probe. This new probe would be a flying chemistry lab. As it descends, it would sniff the air using mass spectrometers to analyze the composition of the atmosphere with incredible precision. It would look for complex organic molecules, the kind that might be created by biological processes. But why stop at just one probe? To truly understand these worlds, we might need a fleet of them. Some scientists envision deploying multiple probes or even smart balloons that could control their altitude and float within the habitable zone for weeks or months. Imagine a robotic floater of our own, riding the currents, sampling the air, and perhaps even carrying a microscope to look for actual microbes in the water droplets it collects. These future explorers would be our eyes, ears, and noses in the clouds, sniffing out the secrets of the giant worlds. It's a vision straight out of science fiction, but the technology to make it happen is steadily advancing. Sending probes is the ultimate goal, but these are incredibly complex and expensive missions that can take decades to plan and execute. In the meantime, we have another powerful tool in our arsenal, one that we can use right here from the vicinity of Earth. I'm talking about our next-generation telescopes, both on the ground and in space. The technique they use is called transit spectroscopy. When an exoplanet passes in front of its parent star from our point of view, a tiny fraction of the starlight shines through the planet's atmosphere on our way to us. By capturing this light and breaking it down into its constituent colors, or spectrum, astronomers can see the chemical fingerprints of the gases in that atmosphere. With the incredible power of the James Webb Space Telescope, we are already doing this with breathtaking precision. For the first time, we're not just detecting these gases, we're measuring their relative abundances. This allows us to start building a picture of the chemistry on these alien worlds. The ultimate prize would be the detection of a biosignature, a gas that, as far as we know, can only be produced by life. Finding such a signal in the atmosphere of a distant world would be one of the most profound discoveries in human history. It wouldn't be definitive proof, but it would be a smoking gun. So, after this journey through turbulent skies and alien chemistries, where do we stand? Could the colossal swirling gas giants of our universe truly be hiding life in their clouds? The honest answer is that we still don't know. The idea remains firmly on the frontier of science, a breathtaking concept balanced precariously between established fact and disciplined imagination. We have seen that the raw materials for life, the carbon, hydrogen, oxygen, and nitrogen, are abundant in these atmospheres. We've identified powerful energy sources in the form of planet-shaking lightning and intense solar radiation, and tantalizingly, we have pinpointed potential habitable zones, narrow bands where liquid water could exist. The fundamental recipe, it seems, is there. We have also looked to our own world for inspiration, finding life's incredible tenacity in the face of extreme adversity. Earth's own Extremophiles provide us with a catalogue of survival strategies, a real-world playbook for how life finds a way. They force us to broaden our definition of what makes a world habitable. Yet we must also be humbled by the monumental challenges: the crushing gravity, the relentless violent winds, the constant threat of being dragged into a planetary furnace, and the corrosive chemical bath of the atmosphere itself, all present formidable barriers. Any life that could arise in such a place would need to be fundamentally different from anything we know. You might be thinking, with all the problems we have here on Earth, why do we spend so much time, effort, and money asking these huge, seemingly unanswerable questions? Why do we care if there are floating, balloon-like creatures on a planet hundreds of millions of kilometers away? It's a fair point. But the quest to understand the universe and our place within it is not a luxury. It's a fundamental part of what makes us human. It is driven by the same innate curiosity that led our ancestors to explore new lands, to chart the seas, and to look up at the stars and wonder what they were. Asking these big questions forces us to be better. It pushes our technology to its absolute limits, leading to innovations that have profound benefits right here at home. To design a probe that can survive a plunge into Jupiter's atmosphere, engineers have to develop new materials, new computer systems, and new communication technologies. Furthermore, this search provides us with a vital sense of perspective. When we contemplate the scale of Jupiter, the age of its storms, and the possibility of a completely separate genesis of life, it makes our own concerns seem a little smaller. It reminds us that we are all crew members on a tiny, fragile spaceship called Earth, adrift in a vast and magnificent cosmic ocean. The search for life in any form is ultimately a search for ourselves. It's about understanding our own origins and our place in the grand scheme of things. For millennia, we have wondered if we are a cosmic fluke, a unique and lonely accident in an empty universe, or if we are just one example of a common natural phenomenon. Finding life elsewhere, even microbial life, would begin to answer that question. It would tell us that the universe is not sterile, but is predisposed to biology. It would mean that the leap from non-living chemistry to living biology is not an impossibly high hurdle. The spark of life, once lit on Earth, could be lit on countless other worlds. If we were to find life in the clouds of a gas giant, the implications would be even more profound. It would mean that life doesn't need an Earth-like world to get started. This would suggest that life is not just possible, but probable, and that the universe is likely teeming with it in forms so strange and diverse we can barely begin to conceive of them. The story of life would no longer be a single book with one protagonist, but a vast library with millions of different stories, each one unique and precious. It would fundamentally change our science, our philosophy, our religions, and our sense of identity as a species. And so we continue to look up. We build our telescopes, we design our probes, and we dream our audacious dreams. Whether the clouds of the gas giants are barren or home to magnificent floating ecosystems, the quest itself is what matters. It's a journey that takes us to the very edge of knowledge and imagination. It connects us to the cosmos and to the deepest parts of our own human nature. The universe is a vast and mysterious place, and we have only just begun to dip our toes into its cosmic ocean. What we find out there will, without a doubt, tell us as much about ourselves as it does about the stars.